We continue with the derivation of self-inductance. Now here it is self-inductance of a solenoid. We already studied what a solenoid is. So here I am considering a solenoid of length L having area of one turn as A, and also it is having n number of turns. Now the moment I switch on this circuit, a current starts increasing through this coil, and this coil is producing the induction effect, and through that there is a back EMF is induced and the current starts increasing slowly. All that things we know. Now we understood that a varying current is flowing that produces a varying magnetic field inside, and that varying magnetic field is linked with the total area of the coil to produce a varying flux, and all those things that we know. So for calculating the self-inductance, let us start with, as the current I flows through this coil, let's say the moment the current is I, then the magnetic field B inside the solenoid can be taken as mu 0 N I by L. Can also be written as mu 0 small n into I. Okay? And this magnetic field is acting through the axis of this solenoid, and therefore the whole area of the turns will be now linking with the magnetic field normal to the field, and therefore the total area inside the magnetic field will be equal to N times B, and therefore the flux phi linked with the area will be equal to magnetic field B into or B dot N times E, or being those things, the area vector and the field vector are parallel to each other, and therefore you can treat this to be equal to N times B into A. Okay? So by substituting you get the flux phi will be equal to, what is B? Mu 0 N I by L. Total area is N times A. So flux phi is equal to mu 0 N square A into I divided by L. This is the flux phi you are getting. Equation 1 I can take. But by definition, this the flux can also be defined as phi equal to L into I, where L is the self-inductance of the solenoid. And therefore you can compare these two and get L will be equal to, what do you get L equal to? Mu 0 N square A by N. So this is the self-inductance of a solenoid. Now if you take N by L as small n, you can rewrite this as L equal to N by L equal to small n. So N square by L square, and you substitute, multiplying and dividing with L, you will be getting it like this, that mu 0 N square A into L. This also you can see in the textbook. That means Let us analyze this one. If the self-inductance of the solenoid is depending directly on the square of the number of turns, and self-inductance depends directly on the area of the circular turn, and self-inductance is inversely proportional to the length of the solenoid. So in this equation you have number of turns and length included, but here it is number of turns per length and area is included. So take it accordingly. Now here also you can prove that self-inductance in medium is equal to mu r times self-inductance in air or vacuum. So here we have taken the self-inductance in air or vacuum, and if you take the self-inductance in any other medium, then the answer will be this one. Now based on this you can expect many questions depending upon the number of turns and things like the self-inductance of a solenoid depends on what all factors. Or a numerical can be obtained like if the number of turns is doubled and the length is half, then something like that. So it is very important to know the equations perfectly. Alright.